My name is Pavel. I'm a postdoc student in Jürgen Koch's group. And today I'm going to continue the story about MaxQuant applied to DIA. And my talk is going to be mostly focused on the quantification and one application story. I think more stories and how to actually run MaxQuant, how to start MaxQuant DIA. Hamid gonna talk like next tutorial. Okay, cool. So recap. So if we talk about MaxDIA, MaxDIA is really inspired by the idea that let's take all algorithms, all solutions which work well in a DDA world, and let's try to apply it to the DI world. And of course, one of the so for example, feature detection. You can really just easily transfer feature detection from DDA world to the DI world. What's more, you can also, we found out that this is exceptionally good idea to do a bootstrapping in the sense that it's actually equivalent, but we are in DDA, MaxQuant DDA, we are taking first search and main search to improve qualities of searching through the database. But also in MaxDIA, we're using Bootstrap DIA, which also step-by-step improving the search. And of course, we also know that MaxQuant DIA is MaxLFQ is exceptionally good for relative quantification. And of course, this is what will be also nice to transfer on in DIA world. Cool. Also, Jürgen today cover how MaxDIA deals with FDR, and but FDR is not enough. So of course we need to somehow, like we can talk about identification, but of course quantification is a very important topic as well, and we have to really robustly check that. So one of the experiments which you're going to see really a lot through the presentation is multi-species benchmark. So usually it can be the idea of the experiment. Let's say we're making sample A. We're mixing peptides or proteins, or really just peptides, and with some known ratios. So let's say that's 20% of mass of the sample, it's bacteria, 15% yeast, and 65% is human. And we call it sample A. And this sample A, we're going to be measured with 3 replicates. And let's say the separate sample B, will have the same mixture of species, but the ratios of the species is going to be different. As a result, E. coli is 5%. As a result, you see the amount of the peptides from E. coli is reduced 4 times. And yeast is 30%. That means that it was increased in 2 times, but human stays the same. So I'm sorry, I didn't write the citation, but this is from Navarro publication of the multi-center DIA benchmarking Nature Biotechnology paper. Okay, cool. I think Jürgen mentioned that he mentioned such parameter, and which is actually very important parameter, transfer key value. And in order to understand how transfer key value works, let's go through some very basic example. We have 4 samples, and now we focused on the just 3 peptides charge modification unique combinations, let's say A, B, and C. And after applying scoring, after using machine learning to improve the score, and lately to use FDR, we came up with Q value, which is basically the product of the FDR quantification. And for each peptide, for each sample, we have like a quality how well we match the library to the experimental spectrum. And as we see, we have a 0.001, 1% Q value, which is really good. And we have also simultaneously for the same peptide, but in sample 3, we have really high value, 40%. That's pretty high. So in common approach, if we make a 1% Q value cutoff, then we're going to see just 2 peptides in the 3 samples. So peptide A will appear in sample 1 and 4, and peptide B will appear in sample 2. So if we leave the situation just like that, it's going to be actually pretty strict. You see that the peptide A was, as a result, defined just in sample 1 and sample 4, which is not really satisfying us. So we come up with idea of the transfer Q-value, the transfer Q-value which coming after applying actual P-value. So transfer Q-value, for example, 0.3 suggests us that for the peptides which we found in at least one sample, we're gonna take all the rest of the hits, matches, which passing this the transfer Q-value, in this case 30%. So as you see, this peptide A in sample 2 was not passing the actual Q-value, but because it was 2%, but actual Q-value cutoff was 1%. But using the transfer Q-value, we're actually getting that. Also, it's applied to the peptide B from sample 1. So by that, we kind of doing something similar to the match between runs, but in DIA world. And that's actually very important kind of concept. And this is a small brother from DDA world. So, but from another point of view, why did I say Q-value 0.3? Why not? But you can imagine, yeah. So if you're using transfer Q-value 0.01, nothing will change. It's going to be the same Q-value, P-SAM Q-value, and transfer Q-value going to be the same, and it's going to get exactly the same results as described here. But if from another point of view, if we get transfer Q-value 1, that would mean that if we found peptide A and peptide B, we will get all peptides which we identified, no matter which score, no matter which Q-value we have for this all samples where we see good matches, like where we see any match, actually any quality of match, except of course non-values. But I would like to highlight, you will not see in such algorithm, you will not find out at the end peptide C. And so this also brings to idea that transfer Q-value doesn't improve identification rate. It doesn't improve amount of identified peptides or protein groups. But what doesn't improve, it does improve reliability of quantification across samples and improve as a result actually at the end label-free quantification. Okay, but as I said, why exactly 0.3? That's maybe there's a better value, but from another point of view, 0.01, so 1% is high confidence of identification, but a lot of missing values. But if you're using transfer Q-value 0.3, then we have like middle confidence of identification, but we have a few of missing values. So as you see, it's essentially trade-off, and we have to find the sweet spot. And how did we do that? We just took some sample where exactly like sample mixed E. coli mixed plus human peptides plus yeast peptides. And we know the ratios. We know that human is not changing from sample A, sample B, and this have to be in the middle. Escherichia coli have to be on the left, and the yeast should be on the right on known distance, on known ratios. And we really decided to run MaxCon several times with different transfer Q values. And we found out that 0.3 actually shows the best sum absolute error. It shows really good number of valid LQ ratios. And we decided to take it and follow all the rest of the quantification testing with this value 0.3. Also, you may notice this transfer Q value influence a lot on the number of values in average, and it's totally makes sense. If you, for example, take, as I said, transfer Q value 1, then if you have any value, any Q value, if not none, for all samples, then you take all these samples into account. But that's exactly what we see here. So we see this in a measurement of 27 replicates of the same cell line. When using transfer Q value 1, we see really flat line. And but reducing transfer Q value up to 0.01, it really shows that we're getting more and more missing values. And yeah, so now this graph is more or less clear. But what I would like to really highlight, I would like to highlight analogous similarity between transfer Q value in data-independent acquisition world and match between runs in data-dependent acquisition. And why I would like to highlight that's analogous, because it's like, you know, it's like wings of butterfly and wings of the bat. We're basically doing the same. We're allowed to fly, but the origin of these tools is pretty much different. And this is exactly what's happening with transfer equivalent match between runs. We are fighting against missing values, yes, but we're like in the base, in a nutshell, we're different. I was really trying to find out something about potatoes analogous, but unfortunately it didn't work out. So, okay, cool. So that was just the preparations. So we did transfer value done. We prepare raw intensities. Now what we would like to do, we would like to use one of the best solutions which we see in the DDA world. It's for dealing with label-free data, and this is MaxLFQ. As it was obvious from presentation of Christoph, MaxLFQ consists of two steps: normalization and protein quantification. So let's just debrief it. So let's just recap how does it work. So imagine that we have some protein, and from this protein we see the peptide 1, but we see this peptide 1 with charge 2 unmodified and charge 3. And again, for now we kind of remembering how MaxLFQ works for DDA data. So we also see peptide 2, but this peptide 2 coming with the same charge, but one of the version of this peptide is unmodified and another is oxidized. One of the thing is oxidized. And the third peptide is coming alone, unmodified and charged 2. So what's we gonna do? In this case, we're just gonna take intensities of this 5 unique combinations of peptide sequence, charge, and modification, and look at the intensities of these instances on the 4 different samples. So in MaxLFQ-DIA, what we try to do, we try to come up with normalization factors, which will reduce all possible ratios between intensities of the same peptide between different samples. And we're trying to reduce it for not just for one peptide, but as I said, for all peptides. Okay, so now how can we extend this pretty beautiful actually algorithm to the DIA world, to DIA samples? In the DIA samples, on the top of the having MS1 information about peptide identity, we're also going to have information about fragment intensities. And for this example, we are focused on the top 3, but I will make a very important comment about exactly this number, top 3, soon. Okay, for now, we have intensity on a peptide level on the first MS, and we have 3 intensities for 3 different fragments on the second MS. And this is for as a peptide 1, charge 2, charge 3 for peptide 2, modified, unmodified, and peptide 3, unmodified. So what's we gonna do next? So now we are increasing the dimensionality, like amount of rows basically in this table, and we are keeping all together not just precursors like peptide intensities in different samples, but also fragments. As I said, we are taking 3 fragments for each peptide. As you see, there's a peptide intensity plus 3 fragments of the peptide 1, unmodified, charge 2, and we see also peptide 1, charge 3, and peptide intensities, and all 3 fragment intensities. And but basically, the normalization is going to work the same. We're just going to treat all intensities. We're going to compare intensities between samples for the same peptide, for the same fragment. We take one fragment and compare intensities, all ratios between samples. And this is very natural extension of the MaxLFQ algorithm. So, but what's we going to do next? So as you see, for normalization, we actually can use fragment intensities. But for the second step, protein quantification, we're just actually doing totally the same protein quantification as it was for MaxLFQ-DIA. We just now focused on the peptide intensities, but this peptide intensity is going to be normalized thanks to the previous normalization procedure. And we're going to find this normalization factor, we multiply on the intensity, and by these normalized intensities, we're going to find out ratios between samples. But we have to keep in mind that it's going to be several peptides per protein. and we require to have at least 2 peptides. You know, it's not just peptides; it's peptides, peptides and plus modification. So charge. And we are trying to find, we're going to find a lot of ratios, and we're going to take the median of this ratio, and this is exactly going to be ratio between, let's say, sample 1 and sample 2. So we know from another point of view that these ratios are going to be the LFQ ratios of the certain protein from sample 2 compared to sample 1. And we have, as a result, a system of equation, but remember this fact, sometimes we may not have enough intersection. We may not have enough peptide which are intersecting between samples for the same protein. As a result, is going to be non-value, and we cannot do much about that. So, but we're trying to resolve this system of equations, and we come up with LFQ intensities for each protein, and we can see how this LFQ intensities is going from sample to sample. Okay, cool. So, but remember one thing. I told you for each peptide we are taking top 3 fragments. What does it mean top 3 fragments? We just for now we're just taking the top intensity fragments. But why top 3? Can you take more? Can you take less? Is it useful or not? So for this purpose, we utilize some experiments which actually, again, multi-species benchmark. But in this multi-species benchmark, the differences are not like 25%. It's actually difference are really, really small. So like 10%, 20%, 30%, etc. So, and this was not just 3 species, it was 4 species. And this data coming from this publication. So, and we run these samples several times with a different top 1 fragment choice. So if a peptide has 11, so okay, we take 11. If a peptide have let's say 50 fragments, we anyway taking top 11 by intensity. But if a peptide has just 5, but we're taking top max 10, so then anyway we're going to take 5 fragments which we have. So increasing this value further and further, we are actually getting better quantification. And what do I mean by better quantification? For each species, we are quantifying interquantile ranges. So basically, how strongly results are deviating, ratios are deviating from median. And we see that with increasing number of fragments, which we are suggesting for MaxLFQ, the interquantile ranges, some of them stacked, some of them of this interquantile values is actually reducing. That means that quantification is getting better and better. So in the current version, we are taking all available top fragments. Yeah, but from that point of view, there's also a big discussion. Should we take all peptides for the protein quantification, or we have to take some amount of peptides? And as you know, it makes sense. Probably the top peptides by intensity, it's the peptides which are really well quantified, where have really good intensities, and this is very robust results. But unfortunately, we see that's actually more peptides you take, better results you get. And the MaxLFQ is actually MaxLFQ-DIA take advantage of this. Cool. So yeah, but you know, we discussed here different parameters, but conceptually we may quantify DIA experiment using the different methods, quant methods. Let's say precursor. What does it mean? Even though it's DIA samples, we used everything. You used second MS for identification, but for quantification, for MaxLFQ normalization, we did everything just like MaxLFQ-DIA. That means we didn't take any fragments into account. We took just precursor peptide intensities, and we found out normalization then, and then after that we used peptide intensities and normalized peptide intensities for finding protein quantification. But as you see, if we're using just precursor information intensities, we're getting like some of interquantile ranges like around 40. From another point of view, let's not take peptide intensity for normalization at all. Let's just take the top fragments. And what do I mean by top fragments? It's just like we have sample 1, and we have own top fragments. If we're taking we have sample 2, we have another top of fragments, and we can be really different sequences. We can have different masses, and if we are doing that, then what we're also doing, we're actually not taking them all separately, but we are sum up. Let's say we're taking top 6 fragments in a sample 1 and sample 2, and we are summing up, and these values, sum up values, we are using for normalization. From another point of view, we know the masses, we know library, we know to what it's matched. Then we can actually choose not just top fragments, but we can choose the top fragments by annotation. So it means that the peptides, which are, we're gonna take all these samples, sample 1, 2, 3, and 4. We find out all the matched fragments. We sum up intensities across all samples. We find out top top intensity fragments for this peptide, and we're just taking all these peptides. It's going to be all the same peptides across different samples, and they're going to again sum up. That's going to be called top fragments by annotation. You see, we get some improvement compared to top fragments, but precursor is still better. Well, and now it's actually a thing which I described comes in. So now we are really finding top fragments by annotation, these fragments which are the same across samples, where exactly they have the same mass, where same annotation, but we keep them as, we're not summing up intensities of them to do normalization, but we keep them as separate instances. That's what do we mean by LFQ split. We keep them as separate instance, and it's the story gonna be looks like that. This table except column row 1, row 5, and row 9, etc., etc. So we're basically gonna do all normalization step without precursor information, but with fragment information, and LFQ splitted. Each fragmentation gonna kept as separate instance and normalization. But from another point of view, we can do mixed. So we can take precursor intensity, we can take top fragment by annotation and sum up them, and now for each peptide instance, we're gonna have basically 2 values. We're gonna have information about precursor intensities, and second, we're gonna have information about sum up fragments intensities. And you see results actually getting worse compared to the previous, but why? Probably LFQ split is really advantageous. And as we see, it is. So now we come up the thing which we discussed. We're keeping precursor intensities, we're keeping each fragment separately and treating them as separate instances, which helps us to find out better normalization. And this actually works really well. For comparison, we took the spectrum out on 2 different quantification methods, MS1 based and MS2 based quantification, and we see that mixed LFQ split on MaxLFQ performs actually really well for DIA samples. Okay, we made that, but then and all these things actually, sorry, I forgot to tell you that all this data we were orbit wrapped. So all this quantification improvement was done on the orbit wrap data with 4 species. But what's about the another platforms, another vendors? And we found out that on SCIEX we actually perform as well. So on the left side, we use the library, like measured library, DDA library, which was taken from this publication, and again we see some good split between different species. But on the right side, we use discovery library, the library which we predicted, and for some species we actually see the huge boost of amount of valid ratios and identified protein groups, and overall it's actually we see great improvement from the usage of the discovery library. So basically library which we have predicted. And in terms of quantification, you can also check that it's very similar, and that basically shows that MaxLFQ works well, not just on the library, on a library supported library-based DIA experiments, but also on discovery, not on just a measured library DIA experiment, but also on the predicted library. We checked that on a SCIEX TripleTOF, but also we checked that on a Bruker TimsTOF. And there we also see that we're getting usually really either similar, either better for some species results between discovery and library mode, so left library mode, right discovery mode. So we're getting pretty similar results, but with the big advantage of using discovery mode, that we don't need to measure pre-species, big, very deep library for each species which we are measuring. We are really just predicting at once and using it all the time. Cool. So now we can ask a few questions, which kind of arising really very naturally. So first of all, maybe you remember Christoph was describing the MaxLFQ algorithm on DDA on fractionated samples. So, but I have to be honest, the fractionation DIA, so when you are making DIA measurement, not just on a single shot, but on several fractionated samples, it's something not very common. And but the question is, can we actually use the MaxLFQ algorithm, which was extended for DIA samples in the same success for fractionation data? Okay. The second question which we may ask, can we apply BoxCar strategy? And I think we already mentioned really briefly on a previous day what's BoxCar, but the BoxCar, it's basically several windows of the first MS acquisition. So basically, we are not just in normal proteomics experiment. You're taking all peptides which are appearing and you're doing first MS measurement. But there's a problem with that. The problem that if you have very major peptide, it's basically just outshadowing the small express peptides, small intensity peptides. And there's a way to actually fight this situation. You can sequentially may focus on not on the whole full range of the first on the full range of masses, but you can focus on some small window. Let's say it's a bit more complicated, but let's say from 200 until 300, and all peptides which happen to be here, there you're measuring additionally. And it's a bit more complicated, as I said, but the idea of the BoxCar strategy that we are really boosting signal of the low intense peptides. So we are getting way more, way better first MS features. And that's, we believe, can help to DIA. So, and the idea here now, can we also merge BoxCar strategy with on the first MS and the DIA on second MS? And we believe it can help. And you know, let's do rock and roll. Let's not answer for each question separately. Let's go all together and try samples with fractionation and BoxCar. That's exactly what we did. So we have 3 libraries, our single shot measured library, a very deep fractionated library. It's all DDA measured library. And the last one, but not least, the discovery library. From the DIA, actual DIA measurement, we did DIA BoxCar, but we did 2 types. We kind of did like single shot and single shot DIA measurement and fractionated. And in this case, it's 8 fractions. It's pretty deep DIA results. So okay, let's focus first of all on the using on single shot library, which is pretty small. And we see that either we're using single shot DIA BoxCar, either we're using fractionated, the numbers are not greatly improved. So we see 6,000 and like around 6,000 we see for fractionated DIA. So we don't see any advantage of using deep library. But from another point of view, let's look at fractionated library. Does it really improve? Okay, we see more protein groups on single shot DIA, but we see dramatically more protein groups on fractionated samples. That's actually really shows that using the deep library together with deep DIA, it's actually really improving the coverage, like detection dynamic range. From another point of view, let's check discovery and discovery library that we predicted. And we see that, like it's also the same dynamic. For the single shot, we see approximately a bit less compared to the fractionated library, usage of the fractionated library. But for the in the case of the sample deeply fractionated DIA samples, we see actually we see more protein groups on the discovery library, and it's really impressive. So first of all, fractionation on DIA is actually possible, and MaxLFQ deals really well with such situation. So, but you know, as I said, this fractionated DIA samples, we can consist of 8 fractions. That's of course very cool, but can we do it less? Can we, you know, it was a 3 replicates, then it means that's 24 samples. But let's say, can I use just 4 fractions? Then 4 fractions, 3 replicates, 12 samples to measure. That's way less time. Maybe is it really advantageous or not? And this question was actually raised by reviewers during the revision, and we found out that yes. So if you take, basically what we did, we had already fractionated a BoxCar DIA with 8 fractions, fractionated with 1 fraction, basically single shot, and we provided DIA samples with 2 fractions and 4 fractions. And now we are looking at 2 levels of quantification on identification, on the protein groups, on a peptide amount of peptides, and we are looking at 3 instances. So we are looking on single shot library, usage of single shot library, fractionated library, discovery library. Okay, as usual, let's focus on single shot library. And as you see, no matter how many fractionated DIA fractions you're using for BoxCar DIA, the amount of the identified protein groups as well as peptides is not changing dramatically. But if you're looking at the fractionated library and discovery library, you see that more fractions we are using, better results we are getting. And of course, it's going to be going on plateau at a certain moment, but anyway, we see that. And we're just really trying to highlight once more that using fractionation on for the DIA, it's actually very advantageous, but it is advantageous in the case when you're using either fractionated library, either discovery library. But as you may understand, the discovery library comes for free. It's in silico predicted. For fractionated library, you have to spend a lot of time. In this regard, this library looks very advantageous. Okay, but we talk about identifications, but nothing about quantification. Of course, it's a very modest comparison, but we measured 3 replicates, and we can compare resulting LFQ values between proteins, between replicates, 3 replicates which we had. So here we're showing the fractionated BoxCar DIA with discovery library, and we see that like protein quantification is actually very robust. It's the values Pearson correlation R value, it's around 0.99 something, and that shows that we're actually really good in the reproducibility. So, but you know, this was about quantification about between replicates. But what would be really also interesting to see how well our results actually agrees with RNA sequence data, which we can easily obtain for the cell line. So it was, as I remember, it was a HEC cell line. In this case, we are comparing RNA sequence data from a HEC cell line plus fractionated BoxCar DIA samples with different libraries. So the question which I may ask, how many genes we're finding in all 4 cases? First case, RNA sequence data. Second case is when we're using discovery library with this BoxCar DIA samples, when using fractionated, when using single shot library. And you see that 6,000, that's pretty a lot. Cool. So next. The next is a genes, like set of genes which we are uniquely finding just in an RNA sequence data. And maybe this could be the first alarm, what's going on here. But you know, if you look at the distribution of the RPKM values, so RPKM just shows how intensely expressed certain gene. So we can see that actually most of this 5,000 of uniquely identified genes for an RNA sequence were located RNA-seq data were located in a value in a range below 0. And it's well known in the literature that the RNA sequence gene expression which located below the 0 values, it's actually it's transcription noise. These genes are barely expressed, and it's very questionable were expressed at all, actually. And as we see, we also have very few proteomics evidences there, so it's just really support the idea. Okay, cool. But next, we see a group of the genes which we identify on an RNA sequence level on discovery using discovery library and fractionated library, and we see that this set of genes is actually biased towards low expressed genes. And this is quite advantageous because using the fractionated library or discovery library, we can really increase the dynamic range of the genes which you can study. But the next group of genes, it's a 608 genes which we're detecting uniquely on RNA sequence level on discovery discovery mode when we're using discovery library, and we see that's also very much biased towards the lower expressed genes. And yeah, the next one, it's when we're using fractionated library, but you see it's still, especially take into account that you have to spend a lot of time and energy to make fractionated library. Using discovery library, it's actually getting very advantageous because this is just already pre-calculated and you can use that. Okay, and the one story which I found out extremely useful, and it really shows the power of discovery library in silico predicted library in the sense of in the case of the DIA. And this is an example I called multiple cancer samples. So in this article, researchers measured several cancers. In this case, it was just four cancer: ovarian cancer, glioma, adenoma, acute myeloid leukemia. And first of all, if you want to measure DIA samples, you need library. And the researchers decided just to measure a very deep library for each cancer. It was a generated library, deeply fractionated library for the ovarian cancer, done. So it was one library for glioma, also separated library, adenoma, and all these type of cancers. And after making these libraries, we provide these libraries for matching to the DIA results, which also was measured and measured for many different samples. As you see, it was a really laborious process, especially measuring such deep library. But what we are suggesting, and what I did, I just took this data from repository, and I took just DIA results. Sorry, I took just DIA raw files. And I took these DIA raw files, and I provided not 4 libraries, measured libraries, but in this case, I provided just one already pre-quantified, predicted discovery library, and with missed cleavages less than 1. And in this case, I made also PCA plot, and I see that if you take into account topology, basically results are totally the same. We distinguish glioma even a bit better in this case. And I would like just to come, first of all, we are getting the same results without actually spending any time on making very deep libraries. So I mentioned you have 100% of time, and 50% of time you're spending on making library, very deep library, and 50% of the time you're spending on measuring DIA. But what we did. So right now we just took this 50% of time which was used for measuring DIA and providing the predicted library. We got totally the same results. This is a really big argument for using discovery mode, for using predicted library. And on top of that, we're getting 5–10% additional protein groups, which is quite significant. Okay, and basically that's it. So this project would not be possible without collaboration across continents, across labs, and all these people actively participated in all this long process of trying and testing software, coming up with ideas why it's something not working and something working. So, and of course, thank you to all of you guys, and thank you for Cox Group. does MaxDIA work with staggered windowses? And if yes, do we have to be deconvoluted before usage of, or is MaxDIA doing this internally? Guys, sorry, I think I need help. I don't understand what staggered windowses are.
May I take it?
Yeah.
So I'm also 100% sure,
so
but I think it
are
means
these methods applicable for endogenous peptidome, non-digested? So let me think. I think if you provide if you provide a library with, let's say, HLA peptides or endogenous peptidome, or even predicted, I think it should work. It should work pretty okay.
So to my understanding, it means that like the windows are not exactly the same from scan to scan cycle, right? So that like that they're moving a little bit or something like this, but of course in a deterministic way. And that's actually not. So we are at the moment we are assuming that that they are the same in each cycle. So you can do whatever you want. Window sizes don't have to be the same. They can vary. Can also be multiple windows joined together, like you do in BoxCar, for example. But it has to be, each cycle needs to be the same at the moment.
So, but just to repeat, so in one scan, in one cycle, the window size can vary in the width, but and between cycles it should be stays the same.
Exactly, and so if you then even go to TimsTOF, then I mean, then you're not talking about intervals, but about boxes in mass ion mobility. Also, these can be any rectangle you like, basically, right? And they can also have variable sizes and shapes, but from cycle to cycle, they have to repeat exactly